Welcome back to Probability and Statistics 1. We have seen now the definition of a Bernoulli process, and we've studied fairly carefully an example of a Bernoulli process, namely the color sequence process. I'd like to show you a few more examples of Bernoulli processes, and we'll see some of the ideas about the random variables and so on that we've seen before come to play in these examples as well. Let's remind ourselves of what a Bernoulli process is. This is just definition 3.17 we've seen before. It's essentially a process of successes and failures in which successes and failures occur independently from trial to trial, but they occur with the same probability from trial to trial. So we have this family of indicator variables I sub k, which simply denote what happened on trial number k. I sub k is 1 if trial k was a success, and that happens with probability p. I sub k is 0 if trial k was a failure, and that happens with probability 1 minus p. And the assumption is that the family of random variables I sub k is independent in the sense of corollary 3.16. That means you'll recall that simply the probability of any intersection of events involving the I sub k's is simply the product of the individual, the product of the probabilities of the individual events. And so that's what a Bernoulli process is. We're going to look at two applications today. One is to the so-called problem of the points that we've talked about a little bit so far in the course. And the second one is about the occurrence of substrings in binary strings. So let's look at the problem of the points first. This was a problem considered by Pascal and Fermat in their famous 1654 series of letters that's widely considered to be the foundation of the modern theory of probability. And here's how it goes. We have two players. They're playing a best of n games match. So think of two players playing maybe a best of 21 games match. The winner will take a prize of a certain number of dollars. I'm calling it A here. But in the middle of play, the match has to be called off. So the question is, how do we equitably split the prize given the state of play when things were called off? In particular, if player 1 had a certain number of wins, say I wins, and player 2 had a certain number of wins, say J, then how should the prize money be divided? For example, you can think of a best of 13 match when the score is when player 1 has 4 wins and player 2 has 3 wins, when the match has to be called off. So if the prize is $1,000, how should it be divided between the two players? To make it even more stark, you might imagine this. Suppose it's this best of 13 games match, but suppose player 1 has won 6 games and player 2 has only won 1, right? In a best of 13 match, it takes 7 wins to win the match. So player 1 is only 1 win away from the match, but player 2 is what, 6 wins away from the match. So player 1 could justifiably argue that he deserves a lot more than half this prize because in all likelihood he's going to win the game. How should we, make that cut precisely and equitably? So the way that Fermat and Pascal thought about this is kind of interesting. They basically said the following. Okay, let's imagine a new match in which we spot player 1 with his number of wins, and we'll spot player 2 with his number of wins as well, and we'll just start play from that point. Now, player 1, may win this new match, and player 2 might win it as well. But the new match sort of incorporates where we were when the actual match had to be called off. So why don't we imagine a situation in which we play this new match over and over again, And we just keep track of the number of times player 1 wins the match and the number of times player 2 wins the match. The amount that we should award the players in the actual match, Fermat and Pascal said, should be equal to the average amount that each player would win in this imaginary sequence of matches, right? And what that boils down to is basically saying that we should award each player the expected value of their winnings given the number of wins each has when play is halted. So this would kind of address the situation I was mentioning earlier, right? If player 1 has 6 wins and player 2 has 1 in a best of 13 match, then in all likelihood, player 1's going to win the match. And that would be taken into account in this scenario that Pascal and Fermat came out with, right? They would start this imaginary sequence by spotting player 1 with 6 wins and spotting player 2 with 1, and then play the match to conclusion. In all likelihood, player 1 would win, but we would do this over and over again. So a few times player 2 might win too if he had an amazing comeback, right? And at the end of all this huge sequence of matches, we would determine the number to the split of the purse by just looking at the average amount player 1 won in this long sequence of matches in which each was spotted their actual wins. So the assumptions we're going to make in analyzing this problem are that basically assumptions that put it sort of squarely in the corral of Bernoulli processes. We're going to assume that there's a constant probability that player 1 wins any game. We'll call that P. And of course player 2 would win a game with the complementary probability 1 minus P. Notice that this embodies the assumption that no single game results in a tie. So this would not be directly applicable to a situation like, for instance, a chess tournament. In a chess tournament, most of the games actually wind up in ties, and we'd need to modify our model a little bit to take that into account. That's possible, but we're not going to do that here. We're going to think more about situations in which there's no possibility of a tie on an individual game. So you can imagine a game like ping pong here, right? Where each point, you're not going to have a tie on a point. You'll have one or the other player winning each point. Second assumption will be simply that the wins and losses are independent from game to game. So the probability that a given player wins a given game is not affected by who won or lost previous games. Then finally, in the best of n match where n is even, there is a possibility of a tie in the match, right? Even if there's no possibility of a tie for a particular game. And so in that case, we'll say that if the match winds up in a tie, like in a best of 20, both players wind up with 10 wins, we'll just split the prize evenly in that case. So basically the assumptions mean that our mathematical model is going to be a Bernoulli process with success parameter P. So P is the probability that player 1 wins, right? We're basically just modeling everything with respect to whether player 1 wins or not. This is completely general because you could just as well do it with 1 minus P being the success probability for player 2 winning. And so we have a Bernoulli process here, and to do the analysis, the first thing you need to just realize is that in a best of n match, the number of games required to win is just the minimum number that gets you above half, and that's given by this expression m sub w is the floor of n over 2 plus 1. So if you think about this, like for an odd tournament where n is, say, 9, floor of n over 2 would be the floor of 4.5. That's 4 plus 1 is 5. You need to win five games to win a best of 9 match, and that's right. If n is even, this formula is correct as well, right? Like if n is 10, n over 2 is 5, and so m sub w would be 6 here, and you do need to win 6 games to win outright a best of 10 match. Of course, if n is even, you could also have a tied match, in which case the number of wins would just be n over 2. That does come up. We won't consider that in the example we do today, but it's not hard to think about how you would handle that. Now the idea is that if the state of play is I wins for player 1 and J wins for player 2, then in order to win the match, player 1 must win an additional M sub W minus I games before player 2 wins an additional N sub W minus J games, right? I mean, that may be a little bit hard to think about, but just think about this example. Suppose we're doing a best of 21 match in which player 1 has already won 8 games and player 2 has already won 5. Well, it's best of 21, so the first player to win 11 is going to win. That means in order for player 1 to win, right, he has to win 3 games before player 2 wins 6 in order for player 1 to win. So another way of saying that would be player 1 needs 3 wins before he gets 6 losses in order to win the match. So we can think about this in terms of a Bernoulli process, and we arrive, well, the theorem that turns out to be crucial here is this one. In a Bernoulli process, the event that you get W successes before L failures is precisely the same as the event that the trial number of the W success is less than or equal to W plus L minus 1. And so you'll recognize that variable T sub W as the negative binomial variable we've studied in Bernoulli processes. The proof of this theorem is actually pretty simple. It's just kind of a counting proof. We basically need to show that 2 sets are equal. So I'll show that the first set is a subset of the second and that the second set is a subset of the first. So first, suppose we have an outcome in which there are, in fact, W successes before L failures. Assume by way of contradiction that the trial number of the W success were actually greater than W plus L minus 1. In other words, W plus L or greater. If the trial number of the W success were W plus L or greater, that would mean that in trials 1 through W plus L minus 1, there would be at most W minus 1 successes, right? Because the W success came on trial W plus L or later. So if there if there are at most W minus 1 successes in trials 1 through W plus L minus 1, that means there has to be at least L failures, because every trial is either a success or a failure. But if that were the case, then L failures would have occurred before W successes, and that's a contradiction, because we're assuming we're an outcome in which W successes occurred before L failures. Hence, the assumption that the trial number of the Wth success was at least W plus L has to be false. It led to a contradiction, and that means that trial number has to be less than or equal to W plus L minus 1. And so if we have W successes before L failures, then the trial number of the Wth success had to be no bigger than W plus L minus 1. Let's do the inclusion in the other direction. Assume that the trial number of the W success is no more than W plus L minus 1. Then that means there are at least W successes in trials 1 through W plus L minus 1, and hence there can be no more than L minus 1 failures. Therefore, W successes would have occurred before L failures. And we have the inclusion going the other way as well. So that's the proof of theorem 3.18. And as a corollary, we can conclude that if player 1 has I wins and player 2 has J wins before a best of n match is concluded, then player 1's probability of winning the match is the probability that the game number, the trial number of the W's win is less than or equal to W plus L minus 1, where W is the number of wins that player 1 needs to get to win the match, right? The number of additional wins. Remember, he already has I, so he needs M sub W minus I, or W here, additional wins. And L is the number of wins player 2 needs, the number of additional wins player 2 needs in order to get to win the match. So this is a negative binomial probability that we'll be able to calculate, since we know the negative binomial distribution. Let's take a look at an example. When Jesse and Chris play ping pong, Jesse wins a point with probability 0.55. In a best of 21 match with a $1,000 purse, let's suppose that Jesse currently has 6 wins while Chris has 7. What's Jesse's probability of winning the match at this point? And if play had to be halted at the current point in the match, how should the purse be split between the players? Okay, so it's a best of 21 match, right? So the first player to get 11 wins is going to win the match. Jesse currently has 6. That means she needs 5 wins. Chris currently has 7, so she only needs 4 wins. So Jesse's going to win the match if she gets her 5 wins before Chris gets her 4 wins. In other words, Jesse wins if she gets 5 wins before 4 losses. And then by our corollary, that's going to be the case if and only if the time of Jesse's 5th win is less than or equal to 8. In other words, the trial number of Jesse's 5th win is less than or equal to 8. And using our negative binomial calculator, we found that probability is about 0.4770. I've rounded it to 4 decimal places here. And there you see the graph of that probability there. I'm graphing the probability mass function for the negative binomial random variable for the 5th success, and you see the probability that the 5th, the event that the 5th success occurs on or before trial 8 highlighted there. It turns out to be have a probability of 0.4770. So that's her probability. What about her expected winnings? Well, look at the random variable that gives Jesse's winnings. Her winning is going to be $1,000 if she wins the match, and we know the probability with which that occurs. It's that probability we just calculated that turns out to be 0.4770. Or Jesse could win 0 if it turns out Chris wins the match, and we know that probability too would be 1 minus 0.4770. So her expected winnings are just the product of the value times the probability that value occurs, and you sum over all possible values. So you see it there, 1,000 times the probability that she wins plus 0 times the probability that she loses, and that turns out to be about $477, actually $476.96. Chris's expected winnings are calculated in the same way. She wins $1,000 with the same probability that Jess loses, right? 1 minus the probability that T5 is less than or equal to 8. And she wins $0 with the same probability that Jesse wins 1,000. That is probability T to the 5 less than or equal to 8. And we know all those. Turns out that that Chris's expected winnings are about $523, $523.04 to be exact. So if play is halted when Jesse has 6 wins and Chris has 5, then the $1,000 purse would be split with $476.96 going to Jesse and $523.04 going to Chris, and that those numbers are basically just proportional to each player's probability of winning the match had it continued. So a couple of discussion questions. First of all, go to that binomial calculator and just play around with the probability of win, P, and see if you can get it to the point where in the current situation, that is Jesse has 6 wins and Chris has 5, the purse would be split evenly. What would Jesse's win probability need to be in order for that split to be even when Jesse currently has 6 wins and Chris has 5? And then secondly, think about how this calculation would change if Jesse and Chris were playing a best of 20 match instead of a best of 21. And here, what you're going to have to think about is what happens if they actually wind up, tying in the match. Okay, so that is a little introduction to the problem of the points. I wanted to consider a second application, and that's to 0-1 patterns. So what the problem I'm considering is this one. What is the probability that some specific substring appears in a binary string? So for instance, what's the probability that 1011 appears in a binary string of length 7. Another question, the related question, is how many binary strings of a given length contain some specific substring. So for instance, how many binary strings of length 7 contain the substring 1011? Those two problems are related, at least in a certain case. But going back to the first one, I want to emphasize that I'm going to consider it when we're talking about the probabilities here, the probability that a certain substring appears in a given string. We're going to actually consider a more general problem in which the probabilities of zeros and ones aren't necessarily equal. And just a little notation, I'm going to use this sort of funny less than or equal sign to denote the idea that one string is a substring of another. So if I'm thinking about a substring I being contained in a substring k, I'll use that symbol I sort of less than or equal to k to denote that. So the mathematical model I'm going to consider in addressing this problem is going to be, you guessed it, a Bernoulli process with success probability p. So given a specific 0, 1 string I, what I want to find is the probability that that substring I is contained in the success failure string for the Bernoulli process of length n. So as an example, let's consider a Bernoulli process with success probability p up to trial 5. And I want to find the probability that 101 appears as a substring in that string of those first 5 indicator variables, right? And then I want to use that result to find the number of 0, 1 strings of length 5 that contain 101 as a substring. So the event we're interested in is the event that 101 is a substring of that sequence of the first 5 indicator variables. I'm going to denote that event by E, and it's a little bit hard to think about just as one whole piece, but we can write E as an event of three different events, right? I'm calling those E1, E2, and E3. E1 is the event that my desired substring appears in the first 5 positions, starting at position 1, right? So I'm denoting that by 1, 0, 1, XX, and all that means is that, the first value is a 1, the second value is a 0, the third value is a 1, and then the last 2 values in my indicator sequence I don't care about. So 1, 0, 1, XX, and you can write that as in terms of the indicator variables just that way. I1 is 1, I2 is 0, I3 is 1. Similarly, 101 could be a substring of the first 5 indicator variables if it occurred starting in position 2, right? So there would be talking about the event x101x. In other words, don't care about position 1, but position 2 needs to be a 1, position 3 needs to be a 0, position 4 needs to be a 1, and then I don't care about position 5. And then finally, the other way it could appear is that it could appear starting in position 3. So I would have XX101. The union of those 3 events is the event that 101 appears as a substring, right, in the first 5 indicator variables, because it has to, if it's a substring, it has to either start at position 1, 2, or 3. But note, this union is not disjoint, right? Because, for instance, E1 intersect E3 is not disjoint. You could have something in both of those events. So we can't just add up those probabilities of the individual events, E1, E2, and E3. We have to use the inclusion-exclusion result that we saw in Theorem 1.2. Theorem 1.2 says, among other things, that the probability of a union of 3 events is the sum of the probabilities of the individual events minus the probabilities of all pairwise intersections, and then plus the probability of the intersection of all 3. So how would this play out with our situation here? Well, probability of E1 is the same as the probability of E2 is the same as the probability of E3, right? because if you look at it here, E1 is the event that I1 equals 1, I2 equals 0, and I3 equals 1. We can use the independence of the indicator variables in a Bernoulli process to just write that probability as the probability that I1 equals 1 times the probability that I2 equals 0 times the probability that I3 equals 1. And that probability is just p squared times 1 minus p, because we have two 1s and one 0. And similarly, I2 and I3 would have that same probability, E2 and E3 would have that same probability because the events E2 and E3 just all have two 1s and one 0 in them. So the probability of E1 equals the probability of E2 equals the probability of E3 equals p squared times 1 minus p. Now the probability of E1, E2 is equal to 0 simply because the intersection E1, E2 is empty, right? You can't have those happening at the same time because you would have to have trial 2, for instance, both being a success and a failure, and that's impossible. Similarly, E2 and E3 can't happen simultaneously because you'd have to have trial number 3 being both a 0 and a 1. So probability of E1, E2 and probability of E2 and E3 are both 0 because those intersections are all empty. E1, E3 can happen though, right? Because E1, E3 could happen in fact, the only way E1, E3 could happen is if you had 1, 0, 1, 0, 1, right? That's the intersection of E1 and E3, that single success sequence, 1, 0, 1, 0, 1, and that happens with probability p cubed times 1 minus p squared because there's 3 successes and 2 failures. And then finally, E1, E2, and E3 can't happen simultaneously because E1 and E2 can't happen simultaneously. So plugging that into the inclusion-exclusion formula, we find that the probability of E is given by 3 times p squared 1 minus p, then minus p cubed times 1 minus p squared. And so I'm graphing that probability here as a function of p, right? As a function of the success probability, p, here's the probability that 1, 0, 1 appears in the first 5 indicator variables from the Bernoulli process. And there you see it. What I want to focus on here for a moment is what that probability is when little p equals a half. It turns out to be, just plug it in, you'll get 11 over 32. This can actually shed light on the number of 0, 1 sequences of length 5 that contain 1, 0, 1. Because think about this. If little p is 1/2, right, then just plug into the formula and we get, as we saw, 11 over 32 as the probability that 1, 0, 1 is a substring of a binary string of length 5. But because when p is 0.5, zeros and ones are equally likely, all 0, 1 strings of the same length are equally likely. Now since there are 2 to the 5th or 32 binary strings of length 5, that would mean that there are, and since the probability that 1, 0, 1 is a substring of them is 11 over 32, that would mean that there are 11 binary strings of length 5 which contain 1, 0, 1 as a substring. And there they are. But what was interesting is we could calculate that probability without specifically enumerating the set of strings of length 5 that contain 1, 0, 1. So some discussion questions here. One thing to think about based on this result, what can you say about the number of binary strings of length 5 that contain the complementary substring 0, 1, 0? Think about that a little bit. What value of p, the success probability, maximizes the probability that 1, 0, 1 is a substring of that binary success-failure string of length 5? And then finally, you can use these same ideas to look at other substrings, right? For instance, look at the probability that 1, 1, 1 is a substring of the success failure sequence of length 5, and then use that to compute the number of substrings that have 111 as a substring. And then compare that to the example we just did and think about it a little bit. Does it surprise you? Is there anything unusual there? And then finally, you could do this for other, other substrings and other lengths. So find the probability that 0110 is a substring of the success failure sequence of length 7. So there you see two fairly non-trivial applications of Bernoulli processes. We're going to move on, as I said before, to talk about independence in some detail. But I wanted to show you some of these examples before we did that, just to sort of give you a hint of the power and the sort of richness of the Bernoulli model in terms of the kind of questions it can address and so on. So thanks very much for your attention. We'll see you back here real soon. In the meantime, take care.